Imagine standing beside a roaring river as it rushes toward the ocean. The river water tastes fresh, but the vast blue sea waiting at the end is filled with salt. Every second, rivers pour enormous amounts of water into the oceans. So why does the sea remain salty while the rivers flowing into it do not seem salty at all? The answer begins far away from the coast, on mountain peaks, rocky cliffs and rain-soaked landscapes. Every drop of rain starts a slow geological process that connects the continents with the oceans. Rainwater is not completely pure. As it falls through the atmosphere, it absorbs small amounts of carbon dioxide and becomes slightly acidic. This weakly acidic rain flows across mountain slopes, forest floors and exposed stone. Over time, it slowly attacks the rocks and breaks them down through a process called weathering. Inside those rocks are countless minerals containing elements such as sodium, calcium, potassium and magnesium. Flowing water dissolves tiny amounts of these minerals and carries them away. Small streams collect this mineral-rich water. The streams merge into rivers, and the rivers transport the dissolved particles across entire continents. River water therefore does contain salt. It simply contains such a small amount that our tongues usually cannot detect it. A glass of river water may look completely clear, but hidden inside it are microscopic dissolved ions. These invisible particles are already beginning their journey toward the ocean. As the river winds through valleys, farmland and cities, it gathers even more dissolved minerals. Eventually, almost everything it carries reaches the coast. At a river delta, muddy brown freshwater meets the deep blue ocean. The water mixes, but the dissolved minerals do not disappear. The ocean acts like an enormous collection basin. For hundreds of millions of years, rivers have continuously delivered tiny quantities of minerals into it. But rivers are not the only source of ocean salt. Deep beneath the waves, the seafloor is also constantly changing. At underwater volcanic regions, seawater enters cracks in the ocean crust. It is heated by magma, reacts with hot rock and returns through hydrothermal vents. These dark underwater chimneys release heated, mineral-rich water into the surrounding sea. They add and exchange chemical elements within the ocean. Underwater volcanoes, seafloor reactions and material released from Earth's interior have all helped shape the chemistry of the oceans. The salt in the sea is the result of an ancient planetary cycle. Yet the most important difference between rivers and oceans is not how salt enters the water. It is what happens when the water leaves. Sunlight heats the ocean surface every day. Water molecules escape into the atmosphere through evaporation, forming invisible water vapor and towering white clouds. But the salt cannot evaporate with the water. Sodium, chloride and other dissolved minerals remain behind in the ocean. The clouds are carried across the sky by powerful winds. They eventually release their water as rain or snow over mountains, forests and plains. This returning water is fresh because the dissolved salt was left behind in the sea. Evaporation acts like a gigantic natural distillation system. The fresh rainwater then flows downhill, enters streams and rivers, dissolves more minerals and begins the journey back toward the ocean. This global water cycle repeats endlessly. Rivers remain relatively fresh because their water is constantly moving and being replaced. A particular drop may spend only weeks, months or years traveling through a river system. Ocean water remains in the sea for far longer. During that time, evaporation repeatedly removes pure water while many dissolved minerals stay behind. This does not mean that every ocean contains exactly the same amount of salt. Salinity changes depending on climate, rainfall, evaporation and the movement of ocean currents. In hot regions with powerful sunlight and little rainfall, evaporation can make surface water especially salty. The Red Sea and parts of the Persian Gulf are famous examples. Near large river mouths or melting glaciers, the ocean can be less salty. Freshwater dilutes the seawater and creates visible layers, currents and swirling boundaries. The average ocean contains roughly 35 grams of dissolved salts in every kilogram of seawater. Most of this is sodium chloride, the same basic substance found in ordinary table salt. However, seawater is not simply table salt mixed with water. It contains a complex combination of magnesium, calcium, potassium, sulfate and many other dissolved substances. If rivers have been carrying minerals into the ocean for millions of years, a new question appears. Should the sea not become saltier and saltier forever? The oceans do have natural ways of removing salt and minerals. Sea creatures use calcium and other elements to build shells, skeletons and coral reefs. When these organisms die, some of their remains sink to the seafloor. Over immense periods, they become thick layers of sediment and limestone. Other minerals react chemically and form solid particles. These particles settle into dark ocean sediments, trapping elements that were once dissolved in the water. Seawater also reacts with the ocean crust. Some chemical elements are absorbed into underwater rocks, while others are released back into the sea. Tectonic plates slowly carry ocean sediments beneath the continents at deep sea trenches. In this way, minerals can eventually return to Earth's interior. The salt level of the ocean is therefore controlled by a long-term balance. Rivers and geological processes add minerals, while biological activity, sediments and seafloor reactions remove them. This balance changes over geological time, but it prevents the oceans from simply becoming more concentrated without limit. There are also places where fresh water can become extremely salty without being connected to the sea. These are often lakes surrounded by land with no river flowing out. Water enters through rivers or rainfall, but it can leave only through evaporation. As the water disappears, the minerals remain behind. The Dead Sea is a dramatic example. Its shimmering water contains so much dissolved salt that swimmers float unusually high on the surface. Salt flats and white mineral crusts form in similar closed basins when almost all the water evaporates. They reveal what can happen when minerals enter a body of water but cannot escape. A normal river is different because it constantly carries both water and dissolved minerals onward. It does not usually keep them long enough for large concentrations to develop. The ocean, however, is the final destination for most flowing water on Earth. It receives minerals from mountains, rivers, volcanoes and the seafloor. Then sunlight lifts the water back into the sky while leaving the dissolved salts behind. The water returns to the continents, but the salt largely remains in the ocean. So the sea is salty and rivers are fresh because they play different roles in the same planetary system. Rivers are the transport routes, while the oceans are the great collection basin. The next time you watch a river flowing toward the horizon, remember that it is carrying invisible fragments of distant mountains. Grain by grain and ion by ion, the continents are slowly traveling toward the sea. If you enjoyed discovering the hidden science behind our planet, like this video and subscribe to Wonder Atlas World for more fascinating journeys through nature, space and history. Until the next wonder.